Okay, so welcome everyone. Today is our first of its kind, and this is a session which is called Introduction to MLOps. So every week I'm going to be coming live at the same time on YouTube, and my goal will be again to give you a very short nugget about what MLOps means and what it takes to take machine learning products to production scale. So we're going to be talking about sustainable ML models, and so that you can constantly, iteratively, make sure that your product is getting better with time. Not just your ML model, but you're actually iteratively, product is getting better over time. We are going to be talking about data-centric approaches as well. So in case you have any questions, concerns, please do ask in the comment section, and I'll be more than happy to answer them. Okay. So let's start with the definitions of what is MLOps. MLOps is the engineering practice that aims to shorten the ML development life cycles and reduce the delays in AI value streams. Now, what does that really mean? It means that typically you will see that in large corporations, there's always an R&D unit that works on the ML and the AI, and they come up with these new algorithms. And then there is always this DevOps team that is in charge of taking all of this into production. But what we are trying to say is we want to enable these teams who all have the similar ideas of where ML models should be and what it takes to take them into production, so that it's not just one person is handing over their job and saying, okay, now you take it to production, but it's a better knowledge, and it's a better understanding of taking something which is R&D and taking into pre-production and then finally to production. So it reduces the delays that a customer would face in order to get access to a viable product. Now, this is the other definition that has been coined, which MLOps simplifies the gap between AI ML research and production and improves the customer-facing experiences. Now, why customer-facing experiences? Think about it. If you're creating machine learning models, you want people to use it, right? So you don't really want to create machine learning models that are just in their silo and nobody's really using it. So now, if you have, let's say you've deployed it, you have your the front end, it's Flask, Fast API, whatever, and then it has already been deployed. But now, let's say that you want to upload a new version. So and this, I'm just giving you an example. Let's say it's a computer vision use case, and so far you were using YOLO v3, right, for bounding box detection. But now you want to use EfficientNet v7, the one that is trained with the highest accuracy. So do you have to really take down your app and then retrain it and again redeploy? Because that's going to reduce your customers' experience. I mean, they will suffer downtime, they will suffer outage, like the 404 error that you get when you go to a website which is under maintenance. So in this case, what MLOps will do is there are ways to shadow. So we call them canary deployments. And what happens is the second version is rolled out in such a way that the users don't even understand that there's been an improvement, but they just see that their experience has actually improved. So these are ways in which Kubernetes, the whole Kubernetes orchestration, if that can be merged with machine learning, then it can hugely benefit the customer-facing experience for machine learning products. All right. I wanted to put this diagram in the bottom because this is a very commonly understood definition of MLOps, which says MLOps essentially is ML plus DevOps. So it's machine learning and it's DevOps, put together. And what we do in machine learning is, of course, we have data, we use it to model, we have the ML model here. And then in the DevOps part, what you're typically doing is you're creating a plan for it, and then you're ensuring it has to be tested, there has to be verification, right, all of that, and then you work in releases. So DevOps group of people, they work in releases, so releases, builds, and they have to always monitor. You'll see these great dashboards, these are the Prometheus Grafana dashboards, in order to see how the customers are interacting. Is there downtime, is there outage, is there anything that is not correct, right? And in these cases, if these metrics can also be ML-based metrics, then they would know if the model needs improvement or not. So that is what we are trying to do, rather than just looking at a dashboard, which is just telling you how much traffic and if are the people satisfied or not, and are they interacting with your ML app or not. Having other machine learning-based metrics significantly would enhance the quality of the product and also the customer-facing experiences. So that is what we're saying MLOps is an engineering practice. So it is not just a bunch of tools and systems, but it is how you use those tools to, in your complete production cycle to improve the customer facing experiences. All right. Now I wanted to show you the differences between some of the words that is out there. And this is a very common question that I get. What is MLOps? How is it different from AI ops? Then there is data ops, then there is DevSecOps. And all these words are constantly thrown at us. And sometimes I get these questions as well. So let me give you the breakdown of what these are and how they're different from the others, right? So let's start with MLOps. Now, MLOps, like I mentioned, it's an engineering practice, right? But it is geared towards operationalizing ML projects. So again, like I mentioned, if it's, let me give you an example of autonomous drive. So we are trying to make sure that we detect a bounding box around all objects, right? How much time would it take for you to have that object and then, put it into the car? So there's a huge, life cycle that goes into that. But now let's say that you have a better bounding box detection model. Would it take the same amount of time to again roll it out? That should not happen, right? So the next time it should be faster. How would you enable that? So that is what MLOps practice would help bring to you. It enables CI/CD pipelines. Now, anyone who is looking into MLOps, they will get this word quite often. It says CI/CD pipeline. CI/CD pipeline means CI stands for continuous integration, and CD stands for continuous deployment. And IBM Cloud actually has their, they have a lot of content in YouTube itself where they explain these terminologies very well. But what I will tell you is CI, like the word says, you typically in a company, you don't work solo, right? You're a group of people. You're all constantly committing code to a repository. It can be GitHub, it can be a Google repository, it can be an Azure repository, you just name it. It can be GitLab, whatever. So it makes sure that everybody's commits are not interfering with one another. If one person is deleting it, you should be able to see a diff, right? So you should be able to see, okay, if somebody did something, somebody messed something up, you should still be working from the last viable commit. So these are the things that need to be taken care of when you're trying to do continuous integration. And then continuous deployment starts from that repository. So it could be GitHub or whatever else. And then it just puts it to deployment. So examples of CI/CD would be Spinnaker. Another excellent tool that is used for CI a lot is called Travis. But then Jenkins is another method in which you allow for CI/CD as well. So these are all just different tools that is out there. But if you can do manual, you can actually manually create triggers so that whatever is there. So let's say that I come in today, I see a new build has come up for let's say a new SSD object detection model. I just hit a button and then that goes into deployment. So that's what my customers see at the end of the day. So it can either be manual or you can actually do that automatically. And Kubernetes has wonderful orchestrations in order for do that. So there's this Istio mesh, which is a service mesh. So there's sidecar injection, which allows for these versionings and rollouts to happen seamlessly. And again, there is this continuous data pipelines, and there is model training and deployment at scale. So understand MLOps doesn't just mean that, okay, I have a model, I'm done. It never says that. MLOps says, okay, you have a model for now. Now you need to deploy it so that everybody, the customers are using it. Now, let's say we start monitoring and seeing that performances are not good. For instance, again, let's say the object detection. So you have built an excellent object detector for the city, right? So it's skyscrapers, it's people, it's cars. Now, all of a sudden, you've taken your car maybe to a safari in a jungle. So there's no more cars, there's no more people, there are just different kinds of animals. Right. So what's going to happen is in the back end, it's going to continuously find these bounding boxes, but it's going to get confused what labels to provide them. And in this case, what's going to happen is the labels, the probability, the confidence score. If you have not trained with enough, lions and tigers and deers, which typically you don't, you will see the confidence score is going to keep dropping. So if that could be a metric that you are constantly monitoring in the back end, that means it's the confidence score. You will know, okay, I think this model needs to be retrained. And then for those instances, if you retrain and push the new model, then again in your Safari jungle, you'll now be able to detect the objects correctly, right? So these are just few examples in which you need to always have a continuous data pipeline, continuous model training, and again, continuous deployment at scale. Now let's get to AI ops. So that was MLOps. AI ops, again, it involves real-time problem-solving systems with minimal human intervention. Like exactly what the word says. It is AI. So AI means artificial intelligence. It's able to do or real-time problem solving, maybe not real-time problem solving all the time, but real-world problems with minimal human intervention. So it does not require much human support, but it's able to do them on their own. So one example of it is AI for IT ops. So IT services. So let's say that you're using a particular service and you're not happy with it. So you need to file a ticket, right? That's a very common way in which larger companies, they work with their customers. So you file a ticket, but if there can be this artificial intelligence backend that can figure out what domain or what category this query belongs to, then they can help resolve that. So they'll probably connect you. Okay, yours is a hardware issue. Okay, yours is a software issue. Let me connect you with the correct software advice provider or the hardware providers. So in this case, whenever this automated ticketing process is getting solved on its own, then that becomes AI for IT ops. So that's another example of AI for IT ops. AI for AI ops typically does require some big data processing solutions knowledge, because in this case, what you're supposed to do, you're supposed to look at a problem from the whole zoomed out version. So let's say that I'm going on, asking for support, but I'm not using the exact word software, or I'm not using the exact words hardware, but I'm using things like cable, I'm using things like adapter. So ideally, if just looking at the word adapter, just looking at the word cable, this automated system may not be able to see that I actually have a hardware issue. However, if they look at the complete data set, they may see adapters typically fall under this metadata or metadata tag of hardware. And that's why I'm typically looking for hardware support, right? So that's why AI ops typically does require large data or big data processing like Hadoop, MapReduce, so that you can actually go ahead and solve these problems. And again, there can be automation in hybrid environments. Hybrid environment means not just fully automated, but sometimes you can have some manual intervention for people to say, okay, these problems were queried at the end of the day, but the automated system was not able to figure out, was it hardware or software, or do they just need some advice? So in that case, there could be a human, but then the amount of work that the human would do is very little. So that's the reason we call it the hybrid environments. Think about it as a semi-supervised setting. And the last one is called data ops. Now, data ops is actually one of the most common, that's out there. So it enables cost-effective development and delivery of products that require data streams. Now, any machine learning algorithms requires data. We know that, right? You cannot have ML algorithms without data. So again, you need a lot of data, but again, what is the cost-effective way to develop and deliver the products? So that is what the principles of data ops will tell you. It does include data governance. So data governance policies and best practices for data storage, retrieval, and sharing. So can you share all data? So let's say your company is storing customer data. Can you share all of that? Answer is no. There have to be GDPR guidelines. There has to be a lot of guidelines that you have to go by before, let's say that there comes a third party who says, okay, give me your data, I'm going to give you your solution. There has to be some amount of scrubbing. There has to be some amount of compression. Maybe there's a lot of zeros or missing fields, so you need to take them away. And even storage retrieval, you want to store them in a good way so that you can even retrieve them. So that's all data engineering. Whenever you're looking into the data engineering parts of it, you're essentially doing data ops. So that's the practiced by data teams, data engineers, architects, analysts, scientists, and operations, right? So those would be the three differences between MLOps, AI ops, data ops. If you have any questions about these, please leave in the comment or even in the chat, and I'll love to answer them. Okay. Now let's get into the ML production system component. So ML systems, what are the different components that go to it? Now let me tell you, for the ML production, whenever you're taking a machine learning product into production, what are the components that go into it? So typically you will see this kind of figure pops out a lot. And again, this is taken from another source, and you will see this popping up again and again. So again, as you see on the left-hand side, there's configuration, automation, all of this has to do with, the data pipeline. Then again, the ML model is actually a very small component to it. And then you see there is a lot of deployment and service. So if I had to break them down, I would do that in three ways. So first of all, I'm looking at the data pipeline. That means how do I ensure constantly good data or new data that the model needs to learn from is coming in. So the data pipeline is going to ensure that you have, this constant feeding of data into the ML model. After that, then there is a modeling pipeline. I mean, it's not just one ML model that you want, but then you have to make sure that it is analyzed, its performance scores, you have monitored it, and maybe you need to change your model altogether, right? So all these decisions have to be taken care of whenever you are working on the ML or the model pipeline. And then finally comes the deployment pipeline. And in the deployment pipeline, you are taking your machine learning model, you are bundling it up, let's say with Flask Fast API. Maybe you have a Docker, you put it on a Docker container, and then you put it on a Kubernetes orchestration, so Kubernetes server. So all of them now become a part of the deployment pipeline, and then you keep monitoring these Kubernetes metrics so that you know at what time something has gone wrong, and you again, go to fix it, or you again redo your data pipeline. One thing I did want to mention here is you see these two different colors of blocks, right? So there is red and then there is blue. Data-centric and model-centric are two very different approaches. Model-centric says that throw all data at me, and my model is going to keep getting better and better over time. What data-centric says is you shouldn't use all data first, but you should use the data in batches. And how you find these batches, again, there is a lot amount of metadata and lot amount of feature engineering that needs to happen. So even if it's images, you should try to find the higher quality images first, or you should try to find the images where there are these limiting conditions. Like I told you, the example of bounding boxes in cities versus if you are in a jungle, then there are animals, right? So finding that, this is actually a new image, and that's the reason why the performance is not good here. So now let me find other images of similar kind and retrain the ML model. That is what is called data centric, where you're taking the data in batches, but not really taking all data at one time. And in this case, what could happen is the ML model may not even stay consistent. So maybe one day SSD is the best object detector. Maybe another day YOLO V3 is the best object detector. Maybe another day some other model is the best object detector. So you can literally automate this whole process of which model is the best, and again roll that out into a canary deployment to your Kubernetes cluster, right? So that would be your Kubeflow pipeline orchestration if you would want to do that. Next, I wanted to get into some of the principles that is very essential for MLOps. Now, think about it. Whenever you're doing machine learning for just you're building a model and you're doing it for R&D, you have this data set and you're trying to have the best performance on this particular data set, and which is fine. But then all of a sudden for MLOps, now you have to be very cautious about biases or things that you should not do. So that's why in this case is the kind of biases that can occur, we have to be extremely cautious about them. So you want to proactively create a generalizable ML model. So let's see what are the kind of biases that can occur in machine learning models. The first off, we have the reporting bias. Reporting bias means when you are, let's say that you are sourcing from a particular data source, and people who are happy with the product, typically they are not going to go and write a review. That's just the human nature of it. But people who are upset about a product, they're going to go and write the reviews. So in this case, do you really have a good enough understanding of how many customers are happy and how many customers are sad? Because the only reviews that you see are the negative ones. So the answer is no. In this case, reporting bias does exist because the positive cases were not even created. How would you try to avoid a reporting bias? Avoidance of this could happen if you somehow in the part of your system, if you enforce the customer has to enter some words after every single experience. For instance, DoorDash, that's the food delivery app in US. What they do is after every single delivery, you have to enter a few words or at least star rate how your experience was in order to place your next order. In this case, what happens? The good events are also captured and the negative events are also captured. So then in that case, reporting bias gets eliminated, right? Then there is automation bias. That means the tendency to support automated answers over, the non-automated ones. So think about it. We all have, at least, in the Bay Area here, everybody uses home security systems, like the automated alarms. And home security systems sometimes can have false alarms. So that means they can have like a leaf or something, or maybe a plastic bag, or maybe a delivery system came and they say, okay, there's theft. Typically, if I am away from my home and if I see an alarm, I am going to believe it. I am going to say, oh, I'm sure that something happened, rather than saying maybe it was just a false positive, right? So you always have a propensity to say that, yes, I think it's an automated system, I believe it more. But sometimes that may not be accurate as well, right? So these are automation biases. Sometimes we just have to live with them. Then there is selection bias. Selection bias completely, built off of the data that you have sampled and you're using to, create your machine learning models. So sometimes it could happen that the data sample that you have acquired, it has gaps. It does not represent by any means the real situation that you are trying to project here. For instance, insurance is a very good, great use case in US. So let's say that you're trying to figure out how much premium a particular area people should be paying, and in this case, the data that you're using is the income and how many times people have been going to hospital. So you might see that people of higher income group, or the middle and the higher income group, they're actually seeking out medical intervention more. Whereas the people who, there can actually be a lot of people in the lower income group there, but they're getting sick, but they're not going to the doctor as much. And you don't even have that data. So that doesn't mean that you increase the premium prices for everybody, because there are some people who will lose out, who will not be able to get the insurance premium if you increase the prices. So in that case, you have to use boosting or those sorts of practices, so that even if there is one data sample, you give it a higher voice, so that you're not biasing your ML model against that smaller group. Then there is group attribution bias. And this happens a lot whenever you're doing data or feature engineering and using unsupervised learning. In some cases, it's a great thing. In some cases, it's not. So ideally, let's say that you're using this automated resume screening method. And what this resume screening method has seen, that people who come from maybe this particular bootcamp, they were not hired from into this particular company. So they can actually, the automated system can actually build a bias. Next time they see the same bootcamp, it's not going to recommend the same job for you. So, and which is wrong, because maybe that other candidate was just not a good candidate. You are, but then the automated system has automatically learned that, this is not a good match. So, and these could be some group attribution biases that sometimes need to be taken care of, that they do not, translate into something detrimental. And finally, there is implicit bias. So due to the assumptions made about the data, that just may not be accurate. So here the example is, so let's say I'm shaking my head. In most cultures, or at least in US, we say shaking my head means no. But then there are some cultures where shaking head can actually signify yes. So if I have a gesture recognition system and I say shaking head is always a no, but then I deploy it to some other country where shaking head can actually mean yes, then it becomes incorrect assumptions. In this case, you should have a new data for those different localities, and your deployment should actually be on the local data set. Otherwise, a global data set or a global model may not work in this case. Finally, I wanted to stop at this point, and this is the Google WhatIf tool. And what this WhatIf tool does is, it's a minimal coding solution in order for you to detect if there is any biases or if there is anything wrong with a particular data set. So this is what I wanted to show you today. So let me click on this particular link, and I wanted to show you how this goes. So this is the, and again, this is just a standalone example on the UCI census data set. What you will see is, again, here, the data set will look like this, and you can literally interact with each and every sample, right? So in this case, you see x-axis is by the inference score. So let me change the x-axis to something else, let's say age. So this particular data set, it's from the UCI machine learning data set. And this data set, how it is created, it just tells you based off of some features, is it predictable that the person has a salary of greater than $50,000 or not? And if it is yes, then you see them in red. And if it's not, you see them in blue. So typically in this case, you see the age is actually not a good marker because your Y is your inference force. You see the X is actually not a good marker because it's all over the place. But now let's see something else. If you're looking at education, can you find a separation boundary? Somewhere around here, you can definitely see you're getting more of red and less of blue. But let's say hours per week, again, it's very hard to separate that. So this is a good classification problem, and what you can see is just, again, based off of these features, you can literally see if a particular data point is an outlier. Then you can go and see what happened, why was it an outlier, and then learn more about it. If you want to now apply boosting, this is a very simple classifier that has been allowed. You can literally change your classifier, and this can, you will actually see what is happening in the, for this particular, for this special data set. You can even, use the predict commands and everything in order to, work on this particular data set. The other thing that I also wanted to, again, these links are going to be available in the description box below. I will tell you that if you have your own data set, then the Colab is the way to go. What you can essentially do is, just create a copy of it. And then all you need to do is just, so you just do file, save a copy in Drive. And as soon as the copy has been created, all you need to do is, again, first, download, install the widget, get the helper functions. And then whenever you're doing this, read the training data, that's where, let me just say, show me code. And here you will see this is the CSV path. So if you have your own data, just change the path. And then you will have to change the CSV column. So, modify this based off of your own data set. And once you're done here, you see this is what the data set looks like. And this is your final Y label, right? So you need to first specify, what is the column that you want to predict. And once you're done, you are supposed to now convert the data set into TF example, because that is what is compatible with your WhatIf tool widget. And then you do create a train classifier. And again, this is a very simple training classifier that has been created. You can definitely create your own classifiers in there. And finally, I say, okay, let me invoke the WhatIf tool for the train model and see the whole thing in here. So you can definitely change the data set to your own data set. If the data set is pretty large, it will just take more time to get it running. But I just wanted to share this widget with you so that, and this would be very helpful in creating the data pipeline. So let's say, for some reason your ML model is not doing well, you want to figure out why that is. So in that case, going through this WhatIf tool in which you take batches of data, and then you literally look at what the output is, and you are able to figure out, I think this was the reason why this particular sample was an outlier, and can I have more of them so that I do not have sampling bias. So these could be smart decisions you then take so that your data pipeline can be improved. All right, so I will stop at that, and let me see if there are any questions. Hi, Venkatesan, it's great to see you here. So your question is whether biomedical engineers need to know big data and data streaming tools like Kafka. That's a good question. Well, it completely depends on your use case, I would say. So again, it depends on what kind of, so let's say that you have a startup, right? And in the startup, what you're trying to do is, again, you have biomedical data, you're supposed to generate models for them, and then you're supposed to deliver to your products. In these cases, Kafka is more big data solution. So I would say having some knowledge of Hadoop PySpark, if you're using Spark on a regular basis, would be useful. Kafka, not so much, because there all of the data sets typically are in the CSV file formats. But if you're using something like CNNs in order to begin with, then PySpark will give you all of the tools that you require for your work. So I would say, look more into Hadoop and PySpark, Databricks, that library is very useful. So you should be able to, get whatever you require from those libraries. Prajwal, thanks for your question. You said, what tools have you planned for MLOps? Actually, I'll be looking more from the GCP side and more of the offerings from GCP. So some of the tools that I will be looking at is, first of all, taking an machine learning application and Dockerizing it. So Docker is definitely an important part. And then the goal will be also to create Kubernetes cluster. Kubeflow pipelines come after that. And then in order to create a sustainable CI/CD pipeline, how would you use Spinnaker and or even Jenkins? So Helm and Jenkins, put together, how would you do a sample deployment? So all of this will be in small snippets that I will be sharing in the future sessions. I know, Prajwal, you did ask this question about data drift. How do you monitor that? And how do you change your model based upon that? A great example for that is the GRE scores. Think about it. Several years back, at least when I was applying to US, GRE scores were the range were very different. They were out of 1600, and then all of a sudden they became 350, or I think there's 300 or 400 right now. So what typically happens is GRE scores, all schools had their benchmark. So if this score, you can apply to this school. If you have this score, you can apply to this school. But now all of a sudden, when the scores have shrunk, what do you think the automated recommendation system is going to tell you? It doesn't know what to do because the scores are so little, right? So that's why in this case, what you would typically have to do is you will see the prediction, the probability of prediction that this score means this school will go down. Or per batch, you will see the performance, even if you start monitoring it on, let's say, Grafana, or even in weights and biases, you will see that maybe the probabilities were in 0.9, 0.8. Now all of a sudden the probabilities are 0.3, 0.4, 0.5. That's where you know that there has been something is off. And in this case that I told you, it is data drift as well as concept drift, because the correlation between the input and the output are not the same anymore. So in this case, you literally have to retrain. All right. Okay. That's all for today. I will see you guys next time, and have a great session. And until we meet again. Thanks, guys.